Um, Hi everyone. It's a great pleasure to be here, and like all of the other thrusts, like the folks in Thrust 4 that is focused on AI services at the edge, are really exciting about the kickoff of the project. So, pretty much, what is the focus of our thrusts? Well, in the thrust 1 and 2, we're going to develop networking and system support for the next generation networking applications at the edge. What we plan to do in this trust is to finally deliver on this promise of edge supported autonomy, where we can have assured, robust and resilient services and autonomous systems at the edge. So pretty much today we have this huge challenge, and there were some great discussions during lunch, that we have these heterogeneous data sources, that we have large number of large amount of data that is being collected, but how can we use that in real time for decision making? Not something that we're going to store on the cloud and decide in 3 months what is the right model and then to use it in the future, but how can we build these systems that apply AI for coordination, control, decision making at runtime. So the goal of our thrust is pretty much to start putting some of these things together and to exploit the available heterogeneous communication and computational resources in a way that build these autonomous services at the edge that have high assurance, meaning that they should behave the way we intended them to behave when we define them, including strong performance and safety guarantees, both at design, at runtime, and both as in initial system setup as well as the system and environment continue to evolve. And to do that, we're going to develop this kind of a rigorous design and analysis approaches, mostly focusing on safety critical systems. So some of the things that how this fits together with the previous thrust, well, we're gonna exploit the advances in computing, in networking, in AI to develop these types of systems, but we also the needs of these types of services are going to be something that's going to motivate the development of the next generation of computing and networking at the edge. And we have a great group of PIs working on this, and it's awesome to add John Kelly also from NCANT who will be joining this trust. So how do we plan to achieve this? Well, just for organizational perspectives, we split this into 2 different focuses. In order to make decision making, we have to have this kind of robust situational awareness at the edge. How can we make sure that our systems know what's going on in real time? And then how can we use this kind of situational awareness and context awareness for high assurance autonomy that's going to be split at the edge? And why we split into inference and control, actually these are very tightly connected as we're going to talk about. So in the next few minutes, I'm going to just give an overview of what do we plan to proceed before Maria and Morley give more details on some aspects of the work. So as I said, the first part is robust situational awareness at the edge, and it's pretty much motivated by the fact that autonomy cannot do much if it flies blind. So we need to have this kind of accurate representation of what is the situation around the agents, what is the context of the systems, and again. We are talking about a large number of challenges that I believe it's really the right time to start addressing, and some of them are captured here. What we want to do is we first want to move from requiring large-scale data sets, and we want to large-scale data sets that fully and accurately represent the dynamical environment. Can we build these models? Can we update them on the fly with only a few additional samples? Can we move from a single agent tries to sense everything around it and make decisions based on that into using this kind of collaborative sensing approach that will allow us to create this kind of both at the single agent as well as on the system as a whole information about what's going on around us. And how can we operate these systems not only in uncertain environments where a lot of things can happen, but also in these contested, potentially compromised environments where we have to deal with limited access to computation, but what is even worse for these systems when we have compromised information. So what we're going to do here is we're going to talk about, like Maria is going to talk about some of her work on a few shot learning for context sensing. Pretty much the idea is how can we quickly adapt our models, how can we build these systems that it's natural and easy to collaborate for this kind of collaborative sensing. And we're going to look at various different application domains. Two that I'm going to that we initially planned to focus was AR for this kind of human autonomy teaming, and the other one is for smart transportation systems, pretty much the autonomous driving in this kind of Athena enabled environment. So Maria will talk more about some of the aspects on the AR applications. What I want to already talk about is one of the works that actually we started collaborating even before we got the grant. As a part of RSV, we had these great discussions, and we actually had the team from Duke and Michigan have their first paper, and pretty much the idea there was looking at perception vulnerability. And a lot of work has been done when we like, okay, you have camera-based or LiDAR-based perception. What we started looking at is, okay, what happens when we have these multi-fusion modalities? How can we launch these attacks, and what are the limits, some of the natural limits that current systems have? And why do we need to move from a single agent to multi-device collaboration? So in the recent work by my and Morley's group that is currently under review, we looked at some of the existing, actually a large number of existing sensor fusion modules that take camera and LiDAR, for example, and we saw that whilst they are good enough against naive attacks, let's say for threat models where we have this kind of physical attack to insert specific points by placing lasers into the LiDAR system, we can insert additional points, and a lot of these fusion algorithms are can easily handle these kind of naive attacks. But it turns out that if we step back and start looking at what's actually going on there, we have a 2D imaging that camera provides, although with maybe stereo systems, we can move that to some level of 3D, but we have a 2D imaging and we have a 3D point cloud. So semantically, if we look at the 2D image that camera, for example, base perception would select as an object, in the frustum of that object, if we are able to insert the points, those points are going to be very hard to differentiate from a real point. So it's actually, we can use this kind of very simple attack if we launch attacks like in the frustum. This is where the real vehicle is. We add extra points here, and all of a sudden the perception starts saying like, oh, this is where our new vehicle is. It's very hard. The moment we start using sensor fusion, which is standard thing in signal processing, you have more sensing modalities, it's harder to attack. But if we are preserving this kind of semantic equivalence in these types of setup, what we end up having is it's very hard to remove object from a picture, but it's very easy to move it where we want within the system situation, within the environment of the car. So we looked at first at physically showing that this is possible, and pretty much what we were able to show is that in a very simple setup where we have a spoofer, we have a target car, and we have a victim car, and they are moving, we are able to insert the points such that there is no vehicle here, but the spoof points that are being detected are being moving over time. So which means that all of a sudden the victim vehicle will have, although there is no difference in the distance between the target car and the victim car, you'll see also another car moving toward it. And just pretty much the idea behind all these attacks is that now when we move toward autonomy, now when we move toward cyber physical systems, we have to look at longitudinal analysis. We have to think not what's going to happen in one step, but what's going to happen over the execution of these systems. So in pretty much, we can start, the moment we can start moving these objects, we can mess up with the tracking that is done on each of the systems by making these kind of spoofed objects move faster or move slower, which will change the perception of what's going on around it, which then the autonomy will start adapting by speeding up or slowing down. And it turns out that it's really easy with these types of attacks to mess up. For example, this is where the victim vehicle is. This is a parked car, and pretty much we start spoofing the point such that it thinks that the parked car is already moving, and that it's going toward it, and it will start doing some kind of collision avoidance. We've shown that on Baidu Apollo software stack. So we show that on different types of scenarios. So it's really easy to do these types of attacks. First thing that immediately someone would ask is like, okay, but you really need to have this kind of pointing of the laser so that you insert these points. These kind of physical attacks are really hard to do at scale. With these types of analysis, we pretty much showed how easy it is if you have compromised drivers on let's say LiDAR, how they can just with a little information around it, how they can perturb the point cloud that is out there, that it cannot be detected by the things that are going on behind. And again, some of these attacks are not going to be immediately dangerous for the system. But what I really want to emphasize is this kind of longitudinal analysis, the physics behind it. The autonomy stack follows that, reacts to changes in the situational awareness, starts speeding up or slowing down. By the time we figure out that we are wrong, it's usually late. This is one of the things why we've started now moving from this kind of single agent sensing to more of the collaborative sensing, how we can exploit this communication and computation. There is a good thing and bad thing about that, but I'm gonna talk about that in a minute. And this is, for example, one of the attacks that is showing how even though this car can move, when we start spoofing, all of a sudden this one stops, or it shouldn't be stopping. The problem with Baidu's simulator is that Baidu's stack is that it doesn't have vehicle avoidance. So if you spoof a fake object, it'll still go through it, which is actually kind of lame demo. So we had to stop it like this. All right. Switching gears in some sense, when we have situational awareness, what can we do without it? How can we have this kind of high assurance coordination, control, adaptation? How can we have decision making at the edge that comes with strong safety and quality of control guarantees? And there is a lot of work now, whether we talk about shielding, whether we talk about different kinds of removing unsafe executions. None of these systems are going to be 100% safe. So if we remove unsafe executions, our cars will always be parked in front of our garage. So in some sense, we have to have this kind of trade-off between completing the mission, between guaranteeing this kind of quality of control and service, and this kind of safety outcome. So what we plan to do is to provide this kind of a high-level framework that will allow us to incorporate this kind of both safety and mission guarantees as a part of the learning process, such that we can learn these types of coordination and adaptation controllers that make sure that we have these kind of strong performance guarantees even in the presence of attack. Here, I want to somewhat highlight a slightly good thing of working with physical world. And what is that? Due to physical inertia that we have in these systems, you are okay if you mess up 1 or 2 times, as long as you can recover within a certain amount of time, which means that we don't have to have 100% of data delivery rate. We can violate sometimes real-time guarantees that the communication and computation can provide. The care can compromise some of the information. Just to illustrate this, for a while, we have been looking at how autonomy is built. And this is a 30,000 feet view on autonomous systems from low-level control, which is your almost 80s and 90s controllers that is adapting in the state space. Whether we're now moving from PIDs to neural network, it really doesn't make too much difference, to the high-level tactical adaptation and the planning. And we looked at how can we provide assurance across the spectrum of these formalisms and different problems. What is important here is that each of these has to be addressed on each level, but the guarantees, let's say on mission planning, affect the requirements for low-level control. But they also critically depend on communicational and computational resources. And just to illustrate that, I'm going to end up with this video. This is vehicle platooning. We have 3 cars that that follow each other. And what we are doing is we are launching attacks on the second vehicle, on the position of the second vehicle. This one has its anomaly detection, intrusion detection implemented here. And because of the physical constraints, we can find attacks that cannot be detected by this. We have some of the traditional ones, chi-square, SPRT. We also have some of the machine learning ones. These attacks are stealthy. And you can see that the attacker was able to push the hit into vehicle in front without being detected. So now the question is, what happened? Do we need, in security domain, we always were looked at like, okay, you need to protect everything. You are either secure or you're not secure. In this domain, that's not the case. What does this mean? Look at this particular setup. It's the same setup, except that we authenticate every fifth message, which means that the attacker cannot insert one message out of, cannot compromise one message out of 5. 80% of them can be compromised. This is the worst case stealthy attack. As you can see, there is almost no performance degradation. This is not some random attack. This is a computed worst case attack on the performance of this system. It gets even better if we move from 20% of protected messages to 5%, actually every 20th message is protected. This is the worst case performance degradation of attack that wants to remain stealthy. So what does this shows us? When we want to provide this kind of quality of control guarantees for autonomy, we don't need to have these kind of absolute guarantees on the communication and computational substrate that are using to support it. We can deal with less than 100%. The thing here is to provide this kind of, and this is something that my lab is very interested in doing, quantitative trade-offs. How much do you lose for less than 100% of guarantees that you can provide, which is really critical for the Athena setup. And finally, we have a great group of PIs who will be working on pushing this on the edge, but we're really also very interested in illustrating the impact and how well this works. So we're going to work with MCT to show how we can do on real vehicles that have 5G and V2X support for communication and coordination between vehicles, as well as more on powered test beds, where we are going to use both semi-autonomous and fully autonomous drones to build this kind of networking infrastructure. So here, what we're going to have is both the drone's autonomy is going to utilize the infrastructure, but also help establish it. So it's actually, this is something that we really have to work closely with T1 and T2 investigators. And finally, another thing is on this kind of AR facilitated human autonomy teaming, where we have to take into account how does human react to this information, to any errors that AR can provide, and how can we build autonomy to interact with humans, to exploit that, and what are the kind of requirements that AR needs to provide? Can we have this kind of trade-off? Again, we cannot have this fully 100% ideal vision of what the AR can be. How can we build these systems with assured performance in this kind of quantifiable manner of trading quality of control guarantees for what the system can provide? And with that, I would like to thank you. There are two amazing talks from Morley and Maria now to follow. And if there are any questions, we'll be more than happy to answer them.
Thank you.